All right, section 6.7, operations of algebraic vectors in three space. It starts on page 327. Just a really quick review of really all the basic operations you've been working with with vectors in two space. Three space, we've talked about three space quite a bit informally and also formally, and it just involves that third component, not a big deal. The component form, the unit vector form, the magnitude, the addition and subtraction of 3D vectors, multiplication of 3D vectors by a scalar is all just what you think it would be. It just absolutely involves the same properties when it's in two space, except, as I've said, it's a third component, that Z component. It's expressed in a variety of ways. For example, if you have, this might be new for some students, but if you have a vector A, at times you'll express it as A subscript X, A subscript Y, and A subscript Z or Z, just representing the first, second, and third component. We call that vector A. Vector A has components AX, AY, and AZ. Okay, and there's the notation here. I don't think it's hard to, it's very hard to follow. Absolutely, it's very straightforward, but students might see a whole lot of confusion, and you just have to work through it. Okay, just try and figure it out and see how it gets employed here. But just the confusion with the multitude of sort of variables and letters here. But the property is just this. Let's focus on get the multiplication of 3D vectors by a scalar. Okay, we've seen that before. K multiplied by vector A. We just put the scalar K into each of the components, okay, that make up the vector in three space. So really not a big deal. Okay, representation of vectors in three space. Again, not a real challenge here. We've just got three components. So we can represent it as a string of unit vectors, okay, or as components. So in this way or in this way as well. And the first example here is writing the vector P at -3, 4, and 7 as a standard unit vector. So our vector P, okay, as a unit vector would be the vector -3i plus 4j plus 7k, and those are all vectors here. Now we've also talked about this hat symbol, and I'm going to start introducing this back again here. So for unit vectors, okay, we want to talk about, okay, the unit vector, okay, as a vector rather than the vector arrow. Okay, we're going to start seeing this hat symbol. It doesn't change the notation. It simply just talks about, okay, representing vectors in a different way with respect to this unit, okay, or unit one vector. Okay, so what I mean here is a unit vector of length 1. And again, don't worry too much about this notation. Just understand that they're still vectors, so they're a little bit smaller. They all relate back to the unit of 1 vector here. Next slide. Okay, so we've got an example here. We're just going to try and figure out some corresponding points, given a little bit of information. So here's a parallelepiped given points A as 0, 1, and 3, B is given at 1, 0, 2, C is at 1, 2, 0, and E is at 4, 4, 4. So that's this point here, A. I'm given B, I'm given C, and I'm given E, another point here, and I've got to find the coordinates of all the other ones. Now, there's a wide range of ways to do this. I'm going to walk you through one. I don't think there's really one set actual good way to do this. It's just, like I said, a variety of different methods to solve this. We'll start with let's finding point F here. And okay, just to show you some work here, point F is going to be found by figuring out what vector AE is. Okay, because I have those 2 points. Vector AE, okay, it's going to be, I start at A and go to E. Okay, so I take the point 4, 4, 4, and I subtract the point A, 0, 1, 3. Okay, and I'll explain why I chose AE in here in a second. So AE, I've got to be 4, just a simple subtraction, 3, okay, and 1. 4 minus 3 is 1. So those are my components. So what I'm going to do with F, okay, is I'm going to find F, okay, by taking point B, which I'm also given, adding the vector AE that I just calculated and found. Okay, and that's going to be my point F. Now I should write that. I should say F equals. I should really just write it like this. F would be 5, and then 3, and then 3 here. Okay, so the concept here is that I find F by understanding that it's a parallelepiped, and if I can find the corresponding equivalent side, in this case it's vector AE, and then just add that vector to F, using B as my start point, and then get that vector, so using B as my start point, and then adding the same sort of direction vector that's represented by AE, that lands me at point F here, and I get the point 533. Similarly, I could use BF, and BF is also the point 431, and BF is here, and I could use that to find point G. Point G, is the point. I better do it this way a little bit more properly. Is the point C, and C I'm given as 1, 2, and 0, and then I'm going to add 4, 3, 1. That same corresponding point here. So I get G to be 5, 5, and 1. The other ones I got, I'll let you guys work through this. BC, 0, 2, and -2, and BC allowed me to find point D of 0, 3, and 1. I have in my notes. I hope those are what you're going to get here. And then finally FE, the direction vector FE is -1, 1. That allowed me to find H of 4, 6, and 2. Okay, check those please for me. Try these yourself and see that. And as I said, there's no one way to do that. You guys may have your own special strategy to find this, as long as we get the correct answers here. Okay, so we talked about in the last example parallelepipeds and looking for parallel vectors. Hope you notice that if two vectors are parallel, they have the same components. They're going in the same direction. Now, they might be a scalar multiple of one another, and that's what the definition is all about here. Okay, so two vectors A and B are parallel if there exists a scalar multiple such that I can make an equality here where the vectors equal each other, but based on this scalar multiple. And the scalar multiple could be 1, right? So it really doesn't matter what that factor is, but it can be just some sort of multiple. Note that parallel vectors can be in the same direction or they could be in the opposite direction. So we should account for that, and we take that negative sign to represent an opposite direction. We take that out of the vector and put it in the scalar. So here's an example where we're going to prove that these two vectors are parallel. Now, as you look at this question, you're going to notice something right off the bat. You're going to notice a sort of a feel to these vectors. It looks to me like vector A and vector B. How are they related here? So how can I make this statement true here? Well, if I have vector A, and that's 2, 4, and 6, it almost looks like I've got a common denominator. I could take out a 2, right, and be left with a 1, a 2, and a -3. Now how does that relate to? Sorry here. How does that relate to vector B, where I've got -1, -2, and 3? It's really close, isn't it? I could take out a -1 here and have 1, 2, and -3. So it almost looks like these are identical vectors now, or certainly this part of the vector. There's some similarities. So they're connected. The vectors are connected by a factor of, what are they? By a factor of what, -2? Does that make sense? So I haven't really proven this yet, but I've shown that it is the case here. And that's kind of the discussion a lot of students have. They look at this, and I said that earlier. You see something, right? You have a feel that they're connected in some way. mathematically, how do we say that? Okay, well, I can say that like this. If I multiply negative 2 times b, I get vector A. Does that make sense? Okay, so if I multiply vector b by negative 2, okay, I get negative 2 times negative 1 is 2, negative 2 times negative 2 is 4, and negative 2 times 3 is negative 6. Now, written a different way, more like my definition here. So there's my scalar. Okay, so in theory, okay, but the point was, okay, A and B are parallel. Okay, now theoretically they are going in a different direction, right? They're going in a different direction. A is double the size of B, okay, and they're going in a completely different direction because of the negative sign, but they're parallel. Okay, it doesn't matter what the size is. If you have one's double the other in length, that's fine, they're still parallel. If they're going in an opposite direction, they're still parallel. Okay, students can also see it this way. Okay, they can say, well, A, negative a half A is B. Okay, so if I take negative a half of 2, I get negative 1. If I take negative a half of 4, I get negative 2. And negative a half of 6 is positive 3. So I certainly can write it like this as well, too, right? I can write that, or just rewrite it in a different orientation. Now, if I turned around and solve for A, okay, I get my same line here. But certainly, okay, this is fine here. I don't think, okay, it matters really what order you talk about the two vectors. Another way to say this, okay, is that B, okay, is negative 1/2 of A, right? And that's fine. This is the conclusion, okay, that we came up with. Okay, that's the whole point of that example here. All right, the concept of collinear vectors. Okay, collinear means to lie in the same line. Okay, so vectors can either be collinear or non-collinear. Okay, or meaning not collinear. Okay, so basically, yeah, vectors either can lie in the same straight line, or they don't lie in a straight line. That's pretty straightforward, I think. Okay, so vectors that lie in, or they're on the same line, they must be parallel, and that's going to be the key here. But again, they can go in, they can go in opposite directions. Okay, certainly parallel. We're checking for parallel. Okay, so we're checking, okay, for parallel, but we can also understand that vectors can go in the opposite direction. Okay, so prove that. Okay, well these are collinear, okay, and this example here is non-collinear. I think I have an example here. Okay, 3 points are, okay, and 3 points A, B, C are collinear. Okay, if that holds here, okay, and it could be, B doesn't always need to be the connecting point. It could be another point here. I think I've got an example. It might be on the other side here. Yeah, so prove that A, B, and C are collinear. Okay, so I'm going to, okay, try and set up a situation here, okay, where I'm going to go AB, okay, is equal to KBC, okay, and K incorporates the factor that it might be negative, so they might be going in a different direction, and one might be bigger than the other, but as long as that's the case here, I should be fine. So I need AB. First of all, I should have found AB. Okay, AB is negative 1 take away 2, that's negative 3. 0 take away negative 1 is 1, and 2 take away 0 is 2. And I'm also going to need BC. Okay. So my BC involves, okay, starting at point B and ending up at C. So I take C, 0 take away negative 1 is 1, 1 take away 0 is 1, and 2 take away 2 is 0. So that's the point. The vector BC is represented by the components 1, 0, and 1. Now, you can find AC. We don't need it in this proof. I'm going to show you an alternative way to do this, and while we're at it, let's find AC. So 0 take away 2 is negative 2. 1 take away negative 1, okay, is positive 2. Okay, and 2 take away 0 is 0. All right, so let's get back to this example here. Okay, so what this question is asking, is there a scalar multiple that a value for k that this statement is true? Okay, so I think, again, some students will see this right away, that it's not going to be possible. There's no way I can create or write a connecting statement here where k equals some sort of number, okay, one single number here that allows these two direction vectors to be the same here. So I would need this, right? Okay, I would need -3 equal k. I would need 1 equal k. And now all I'm doing here is this, equating components. Okay, and I would need 2 to equal 0 times k, right? K times 0, or 0k. Okay, and I can write it like this if I want. Okay, I don't normally write my 1. Okay, and that would be 0. So look at my questions here. So I've got okay, oh, sorry, +3. And this one I've got k equals 1. So right away there's an inconsistent solution here. Okay, I've also got it here, 2 equals 0. There's no way that ever happens. So there's an inconsistent solution straight across the board here. What that means is that there's no value of k, okay, that allows for this to be true. Okay, so that's it. Are they collinear? Okay, they're non-collinear. They do not lie in a straight line. Now we could have used AC. I calculated AC. I could have used it in here or in here. Okay, but I want to go back to looking at my 3 direction vectors here. Is there any way that these 3 direction vectors are going in the same direction? And all you have to do is sort of look at factors here. When there's a lot of 1s and a lot of 0s, chances are there's no way I can get some of these things here. BC and AC are close, right? They're common. Okay, it almost looks like it's multiplied by 2. Okay, but this little negative sign throws that off. It looks like it would be, and in fact, if there was no negative sign, if it was +2, yeah, AC is just double BC. Okay, but that might help us figure out that some of these are parallel, right? These two vectors BC and AC might be parallel, given that was plus, but there's no way point A, that is also part of that. And they might be parallel, but they're certainly not connected. They don't follow in a collinear type of line here. Okay, the next, that's it. I think, that's it for this kind of work here. I don't know if I've got, I'm going to pause this. I think we might be right onto our homework questions. Okay, I might pause this and get back here. No, we are good. In my notes, I've got a question, but it doesn't look like it's in the lesson here. I may post it again and sort of see if I can track it down from in the chapter here. All right, good. Good luck with the homework. It's pretty straightforward, and we'll get back to you in section 6.8.